We have a liquid temperature control system over here on the left. This is used to control the temperature of the liquid within this tank. It has an built-in air coil with an airflow of QA and an air temperature TA. And the purpose of the system is to bring the temperature of the liquid inside this tank to the desired value as fast as possible and keep it at that desired level despite of the outside temperature and of any perturbations that might occur. Now, in order to understand this system, we must first understand the basic physics of the system. The problem is that thermodynamics can be a very complex domain. This example that is described here is very different from the one that I describe here. So from the liquid temperature control system that I described in this movie, but I will use this example here to show you what the relationships will look like. So for heat transfer functions, the relationships can be very complicated. It can look like this over here, and it will take some time to understand them properly. That's why I'm not going to go into such detail, and I'm going to use simplified relationships for the equations of heat transfer for this liquid temperature control system. And I'm just going to take it very fast and step by step for our system here. Now, as we know, we have our airflow, which has a debit. I'm not of QA. I'm just going to call it airflow from now on, and an airflow temperature, which I'm just going to call temperature from now on. So both QA and TA. And now we have to think about the quantity of energy transferred from the air coil to the liquid per unit of time, which will be directly dependent on QA and TA. And we will presume that the tank is perfectly isolated for now, and there is no energy loss at the tank surface. So the quantity of energy transferred from the air coil to the liquid is equal to this relationship over here. Now the quantity of energy transferred from the air coil to the liquid per unit of time, which is this over here, is equal to a constant times the airflow. And the higher this constant, the better the transfer. So this is a constant depending on the material out of which the coil is built and other factors. And it characterizes the way that the airflow transfers its heat to the liquid. And the same goes for KTL. So it's very obvious that the quantity of energy transferred from the air coil to the liquid per unit of time is directly proportional and to these four values, to these four variables. And by transforming this relationship into the infinitesimal domain, we have this relationship over here. This is a usual transformation when we go from finite quantities to infinite small quantities. And as you can see in the second relationship, we now have all the parameters dependent on time, and now QA and TA are obviously time dependent, as these can be increased or decreased as we wish. But the question is, why are KQL and KTL time dependent? This is easy. The closer the liquid temperature gets to the air temperature, the less influence the air temperature has over the liquid temperature, which means that KTL approaches zero. Even more, if these are equal, there is no more energy transfer, which means that KTL is exactly zero. And even more, if the liquid temperature somehow gets higher than the air temperature, then the air will cool down the liquid temperature, which means that KTL will become negative. Okay, now let's go further, and by multiplying this relationship over here with dt, we obtain this relationship over here, and by integrating this, we will obtain the exact value for the energy, for the extra energy, let's say extra energy transferred so far from the airflow to the air tank, which depends of course of the initial energy that was contained in the liquid, and plus the integrals from the initial moment up to the current moment of the other two components. If we were to go into more detail on the exact formula for KTL, this will be also directly proportional to another constant, to a heat transfer constant between the liquid and the air, and also on the difference of the air temperature and the liquid temperature. As I said before, if the air temperature is much higher than the liquid temperature, it will transfer much more heat to the liquid. If it's lower, it will cool the liquid down. That's why KTL will be negative. But for the moment, we leave it simple and just leave KTL as over here, and I will detail KTL later on in the simulation. Okay, now the final part, let's just express the temperature. So for this, I'm going to make just the simplifying assumption that the liquid is perfectly stirred. So we could have here a mechanical device that's stirring up the liquid. So I'm making the simplifying assumption that the liquid is perfectly stirred, and the temperature is evenly distributed throughout its volume. In this case, the temperature is directly proportional, so the temperature at any time t is directly proportional to the liquid energy and inversely proportional to the liquid mass. So there we have our temperature formula. I'm going to zoom in a little. So this is our uh, temperature formula over here. Okay, so how to simulate? And it takes the liquid about 15 seconds to reach this temperature. Let's bring our system more closer to reality and presume that the tank is not perfectly isolated. What happens in this case? Well, to see that, let's go back to our initial relationships. So we have here this formula over here. And this will be, I'm going to use copy paste. And it's just going to be another integral, but this time between the surface and the outside environment times the liquid temperature minus the outside temperature. This is not as complicated as it looks like. Now, if we look at our formula, this is what the energy now looks like. It has this additional component, and actually I've done a small mistake here. This is supposed to be a minus. And what this changes in our system, now that the environment also influences the liquid temperature inside the tank, is that the liquid temperature will not be able to rise anymore to this step input over here at 50, because it will constantly lose energy at the surface, so it will constantly lose temperature in the entire volume of it. How to model this? We must see that the formula for our energy has changed. So it has this extra component over here. I'm going to assume that KSO is a constant, and I'm going to add this component over here like this. So we need to get the difference between the liquid temperature and the outside temperature, and for this I'm going to use a sum block again. The plus and the minus. And what we now have here, we are going to assume that the outside temperature is, let's say, 20 degrees. No, let's not make it as the initial temperature. Let's change it to 10. So now what we have over here is TL, so the liquid temperature, minus the outside temperature. And let's place our constant KSO over here. Let's give it a value of 0.1, which is enough. Close the connection. And let's place the integral block over here. Let's see what the system behaves like now. And sure enough, it can't reach the value of 50 anymore. Because now the outside temperature also has an influence over the liquid temperature. And as long as the outside temperature is lower than the desired temperature, the liquid temperature will never be able to reach the desired temperature using this system configuration. Therefore, we need a controller to do this. Let's now build a controller for our system. For this, we will have to, in order to do this, we will have to add a controller over here and control these two variables, the airflow and the temperature. To do that, let's build a subsystem first. So I'm going to place this entire system as a subsystem. By looking inside the system, we can see that the system is the same, and over here we have the airflow and the temperature. And I'm going to rename this to make sure they are displayed correct. And outside we have the liquid temperature. I'm going to save it. So this is our subsystem. Let's build a PI controller. I'm going to leave this system here as it is. So we can compare it with the control system. So this will be the uncontrolled system. And I'm going to place the steps again. And I remember we had a final value of 0.1 for this and a final value of 50. And inside here we have the outside temperature of 10 and the initial temperature of 20. And this will be our control system, which will have two PI controllers. a negative feedback loop. Actually, two of them. A desired value of 50 for the temperature. And the purpose of, actually, another purpose of the control system is to eliminate the perturbations. And a perturbation, now a perturbation might be if the outside temperature would change at, let's say, 30 seconds, at 30 seconds by 30 degrees, for example. And to simulate that, I'm going to place a step inside the model over here, which at the step time of 30 seconds will have an extra 30 degrees, and since the outside temperature here has a minus sign, we will have to place it with a minus sign over here. So what I am now actually doing is, at 30 seconds I'm increasing the outside temperature by 30 degrees, and let's see how the system reacts. And sure enough, we can see that at 30 seconds exactly the outside temperature has changed, and the liquid inside the tank has gone up to 50. But what if the outside temperature was to increase by 70 degrees? The temperature inside the tank will go over the desired value of 50, which in a critical application is not allowed. Now I'm going to use the same system here again. That's why I'm going to delete this old one, place the system with the perturbation here as well, and let's see how this system now behaves. As a measurement element, I'm going to use a gain block of 1, which doesn't change anything, but we have a measurement element. I'm going to use the same for an execution element. And I'm going to close the negative feedback loops, sorry. And let's take a look at how the control system behaves. But first of all, this is not a PID controller now. Actually, not a PI controller, because a PI controller looks like this. And normally one should one should make sure that that the parameters of the PI controller are calculated according to some criteria and performance requirements. Let's simulate this system too, and sure enough we can see that it maintains a constant value of 50. Let's make a comparison between these two systems, and to do that I'm going to place them together on one scope. For that I'm going to use a multiplexer. I'm not going to use this scope anymore. The first difference that we can see is the perturbation is almost not felt at all. If we look over here, we know that our desired value of temperature is 50. The uncontrolled system can't reach that value, and after the perturbation it even maintains a higher value, whereas the control system keeps a very steady value, and the perturbation over here at 30 seconds is not even felt at almost at all. Let's now adjust the parameters of the PID controller for a better performance. For that I'm going to compare the uncontrolled system with the control system again, and to give the uncontrolled system a fair chance I'm going to start the two inputs at 0 both, and I'm going to perform the simulation again, and as we can see, just like before, the uncontrolled system can't reach the value of 50, and here we have a perturbation, but this time we have a positive perturbation which is not felt by the control system. Either way, this is not what I'm looking for now. This time I'm looking to increase the performance of the control system to make it control the temperature faster. And as we can see here, in both cases both systems need about 10 seconds to reach a stable value, and it sometimes this is not enough, so I'm going this time to adjust the controller parameters, and for this I'm going to copy paste this system and place a third one but for this one I'm going to adjust the PID parameters. I'm going to place them as 10, and sure enough the third controller reacts much faster, but to be fair, I'm going to place a saturation on the controlled variables, because you can't have an airflow higher than 0.1 and you can't have an air temperature greater than 200. And still, even with these saturations, the second controlled system controls the temperature with a much greater performance, as we can see over here.